This $9 billion system is running out of water. One of the most important river systems in North America is running out of water. Along the Columbia River, a $9 billion system is coming under pressure as water levels continue to fall. In 2023, water levels at parts of the basin dropped to some of the lowest points recorded in decades, forcing operators to reduce output at multiple hydroelectric facilities. What was once a reliable natural engine, powering millions of homes, supporting vast agricultural regions, and sustaining critical salmon populations, is becoming far less predictable. To outsiders, the river still looks the same, a blue-green artery winding through cities and landscapes. But behind the dams, the balance is shifting. Snowpack is declining, demand is rising, and climate patterns are no longer stable. The system was built on one key assumption, that there would always be enough water. That assumption is now breaking, and what was once a stable system is turning into a constant balancing act. Which raises a difficult question, not just how much water is left, but what happens when there isn't enough for everything anymore? Because that moment may already be here. How the Columbia River hydropower system works. The Columbia River is no longer just a river. It's a machine, a vast network of dams, reservoirs, and control systems stretching across hundreds of miles, regulating one of the most powerful waterways in North America. 8 major dams on the lower Columbia and Snake Rivers alone generate electricity for millions of people. In fact, the Columbia River Basin supplies over 40% of the Pacific Northwest's hydropower, making it one of the most energy-critical river systems in the United States. Water is held, released, redirected. Not by nature, but by design. Every drop is tracked, every flow is managed. At least, it used to be. Because this system wasn't built for uncertainty, it was built for predictability. Snow would fall in the mountains, spring melt would refill reservoirs, water would arrive on time, every year. And from that rhythm, everything else was calculated. Power generation, shipping routes, irrigation cycles. Entire cities, entire industries built themselves around that reliability. At its peak, this system supports over 8 million people and irrigates millions of acres of farmland, turning dry regions into some of the most productive agricultural zones in North America. But now, that rhythm is breaking. Snow arrives later, melts faster, or doesn't come at all. In recent decades, scientists have observed a steady decline in mountain snowpack, in some areas dropping by more than 20 to 30% compared to historical averages. That snowpack isn't just frozen water, it's storage, a natural reservoir designed by climate and elevation that releases water slowly over time. So what happens when that reservoir disappears? What happens when the timing shifts and water arrives too early or not at all? And the system, no matter how engineered, can't fully control what it depends on. Because beneath all the infrastructure, all the technology, all the planning, there is still one thing it cannot replace: water. Water shortage crisis. Power, farming, and shipping competing for the same river. The real pressure on the Columbia River system isn't just environmental, it's competition. Because this river isn't serving one purpose, it's serving all of them at once. Power for millions, water for agriculture, a major shipping route, entire ecosystems, all from the same source. And now, there isn't enough to do it all. So every decision becomes a trade-off. More water for salmon migration means more water spilling over dams, and less flowing through turbines. Less power, higher costs, more strain on the energy grid. In peak demand seasons, even small drops in hydropower output can force utilities to buy electricity on the open market, often at significantly higher prices. For agencies like the Bonneville Power Administration, those losses are already reaching into the billions. But the impact doesn't stop at electricity. Shipping depends on stable water levels. The Columbia Snake River system moves millions of tons of grain every year, much of it exported globally. When the river drops, barges carry less cargo to avoid running aground. In some cases, a loss of just 1 foot of river depth can reduce a single barge's capacity by over 10,000 tons of cargo. A single inch of lost depth can mean thousands of tons of cargo left behind. Transport slows, costs rise. Agriculture faces the same pressure. This river irrigates millions of acres of farmland, supporting crops that feed both domestic and international markets. In dry years, water allocations tighten, and some fields aren't planted at all. Which raises a deeper question. What happens when water scarcity starts to affect not just local farms, but global food supply chains? So the consequences spread outward, from dams to power grids to farms to global markets, all connected by the same constraint: less water. And the system was never designed to choose between them, because it was built on abundance, not limitation. But now, every drop has a direction, and every direction has a cost. And in a system this interconnected, every decision creates winners and losers. So the question changes, not just how to manage the river, but who it's for, and more importantly, who decides.
Salmon collapse: how dams and water shortages are pushing ecosystems to the edge.
Eventually, the system reached a point where it could no longer decide for itself, so the courts stepped in. In 2025, a federal ruling forced a major shift in how the river is managed. The reason was simple and alarming. Wild salmon populations were collapsing. In some cases, down more than 90% from historic levels. Some runs that once numbered in the millions now return in the tens of thousands, or less. Despite decades of solutions, fish ladders, hatcheries, bypass systems, the decline hadn't stopped. Because for salmon, timing is everything. They depend on cold, fast-moving water to migrate downstream to the ocean, and years later, to find their way back upstream. But today, rivers are warmer, slower, more fragmented, and each dam they encounter reduces their chances of survival. In some stretches of the river system, only a small percentage of juvenile salmon successfully make it to the ocean. So the decision was made. More water must be released. Not for power, not for shipping, but for survival. 8 major dams were ordered to increase water spill from March through August, sending massive volumes of water over the dams instead of through turbines. The idea is simple. More spill means faster currents and a safer path for young salmon. But that decision comes with trade-offs. Every gallon of water diverted away from turbines is energy that isn't generated. During peak seasons, that lost power can equal the electricity needs of hundreds of thousands of homes. Less reservoir control means less flexibility during drought conditions, and less stored water means greater risk when dry years hit harder than expected. So the system changed, but only partially, which raises a difficult question. Is this enough to save the salmon, or just enough to delay what's coming? Because now, the river isn't just balancing nature and industry, it's balancing legal mandates against physical limits, and those limits don't negotiate. And if the water simply isn't there, no ruling, no system, no amount of engineering can create it.
Why current solutions to the Columbia River crisis are failing.
For decades, the answer to every problem on this river was the same. Build something, fix it, engineer around it. Fish ladders helped salmon move upstream, bypass systems guided them downstream. Hatcheries released tens of millions of fish every year to compensate for declining wild populations. And for a time, it seemed like it might be enough. But over time, a pattern emerged. Every solution solved one problem and created another. More water spill helps migration, but reduces hydropower. Hatchery fish increase short-term numbers, but can dilute genetic diversity, making wild salmon less resilient over generations. Engineered systems improve passage, but can't replicate the complexity of a natural, free-flowing river. And even with all these interventions, overall survival rates remain low. So each fix adds complexity, adds cost, adds uncertainty. Today, maintaining this system costs billions of dollars annually, with no guarantee of long-term success. At the same time, the environment is changing faster than the system can adapt. Warmer temperatures increase disease risk in salmon. Lower flows concentrate predators. Shifting seasons disrupt migration timing that evolved over thousands of years. Problems this infrastructure was never designed to handle. And even the system itself is starting to show strain. Aging dams, operational limits, moments where precision becomes harder to maintain. Because no matter how advanced it becomes, it still depends on something it cannot create: water. And increasingly, predictable water. So what happens when unpredictability becomes the norm? When solutions can no longer keep up with the speed of change? When each fix only buys a little more time? Because at some point, this stops being an engineering problem and becomes a limits problem. And when that happens, every solution becomes temporary. Every improvement becomes fragile. And the question is no longer, how do we fix the system? It's whether the system can still be fixed at all, or whether we're watching a system designed for stability slowly lose it.
What happens if the Columbia River system runs out of water?
What happens if the system stops holding together? Not all at once, but gradually, one season at a time. A year with low snowpack. Reservoirs don't fully recover. Water levels drop just enough to force smaller decisions. Less power, higher prices. Then another year, hotter, drier. In some recent seasons, parts of the basin have already seen record low snowpack and earlier melt cycles, shrinking the window when water is available. Shipping slows, agriculture tightens, energy demand rises, but hydropower can't keep up. So utilities import more power, pay more, stretch the grid thinner. During extreme heat waves, electricity demand can spike dramatically, just as water levels fall to their lowest. And across the system, the margins begin to disappear. Less buffer, less flexibility, less room for error. What used to be rare becomes routine. At the same time, the ecological cost accelerates. Warmer, slower rivers push salmon survival even lower. Higher water temperatures increase disease outbreaks, turning entire stretches of river into barriers salmon can't cross. Some runs, already down over 90%, struggle to sustain themselves at all. So every choice becomes sharper. Remove dams and lose energy, navigation, stability. Keep them and ecosystems continue to decline. Invest more and costs rise with diminishing returns. And the scale of those costs is massive, reaching into the billions with no guaranteed outcome. There is no clean solution, only trade-offs that get harder each year. Until eventually, the system reaches a point it was never designed for. Not managing abundance, but surviving scarcity. And when that happens, the question is no longer how the river is used, but what can no longer be sustained. Which systems get priority? Which ones are scaled back? And which ones are allowed to fail? Because collapse doesn't always look like failure. Sometimes it looks like a system that keeps working, just a little worse every year, until the change becomes impossible to ignore.
A warning for the future. What the Columbia River crisis means for global water systems.
The Columbia River system isn't broken. Not yet. It still powers cities, still moves goods, still supports farms and ecosystems. but it's closer to its limits than it has ever been before, and the margin for error is shrinking. Because this was never just a river. It was a system built on an assumption that nature would remain predictable, that water would always be there, enough for everything. But that assumption is no longer holding. Across the western United States, water systems are already under similar pressure, from the Colorado River to reservoirs that have reached historical lows in recent years. And globally, the pattern is repeating. Rivers that once seemed permanent are becoming seasonal. Glaciers that fed them are disappearing. So this isn't just a local problem. It's part of a larger shift, where natural systems are becoming less predictable and human demand isn't slowing down. And now, every decision carries weight. Every drop has a cost. Every solution creates a trade-off. Because in systems like this, there are no isolated consequences. Pull water in one direction and something else gives. So the question isn't just about this river, it's about something bigger. What happens when the systems we depend on can no longer do everything we ask of them? Do we adapt? Do we prioritize? Or do we keep pushing until something breaks? And more importantly, who decides what matters most? Because the Columbia River isn't just a warning, it's a preview of what happens when natural limits meet human demand, and those limits don't move. So the final question is simple. Can this system be balanced? Or are we already watching it slowly fall out of alignment? And if it is, how long before other systems follow the same path? Subscribe for more deep dives into climate, water, and system risk. And tell me in the comments, if there isn't enough water for everything, what should come first? Energy, food, or the river itself?